at the very end of class last time, we just wrote this down. And this is not something that should be new to you. You've heard this before in other science classes. Is that true? Yeah? Okay. Energy is not created or destroyed. Never since the beginning of time. The Big Bang happened, right? There was a whole lot of energy. At the moment right before the Big Bang, there was a whole lot of potential energy. Would you agree? Yeah, right? And then boom, right? And after that, well, then things are moving a whole heck of a lot. So that would be a whole lot of, what kind of energy? If it's not potential, it's probably kinetic, right? And things can change between potential and kinetic. They do all the time. And they change between types of energy too, like all of that big long list that we made a few days ago. But the total amount of energy in the universe has always been the same, will always be the same, will always remain the same. That is the only, thank you, fundamental rule in all of science. Okay? You've learned a lot of other rules. They all come back to this. Okay? In chemistry, I think that they teach you a rule of conservation of matter. Did you guys talk about that with Mr. Schoenberg? Okay. It's a lie. Sorry to break it to you. It's not really true, because sometimes matter turns into energy, and then what? If you've maybe seen this equation, this thing E equals mc squared. Have you heard of that before? Right? So actually everything that has mass has what they call rest mass energy. And so if you talk about it all in terms of energy, then the energy is always, always conserved. Is that kind of okay? Except that I'm telling you that Schoenberg was lying to you, but that's not going to be a whole new thing. You'll get used to that as life goes on, okay? This is the thing. This is it right here that is true in all of science, okay? Energy is always conserved. And the key here is that we're talking about things in a closed system. What do I mean when I say closed system? What does that mean? Sean?
It's like there'd be like nothing outside of the system interacting or adding energy.
Right. So nothing's interacting with it, nothing's taking energy away or adding energy to it. Okay? So if we talk about the frog, and the frog is sitting here, and you look at this situation number 1, and then you look at situation number 2, does he have the same amount of energy? Sitting here and sitting here? That's a weird question, Ms. Carveling. I don't know. What kind of energy does he have right now, if any? You could say he has gravitational potential, couldn't you? If you call your H equals 0 where? The floor or the earth or the center of the earth or something like that, right? Okay. I put him up here. Does he have the same amount of potential energy? Gravitational potential energy? No, he has more, doesn't he? So what's up with that? I just told you that this is the truth. This is the only real thing, and now we just broke it? He has this much energy, right? Or if I call H equals 0 the table, that's going to make life easy. He has 0 energy right now, 0 joules. Does he have energy now? Yeah. Is the energy of the frog conserved? No. Well, let's look. Let's talk about this. He has 0 at the beginning. So here he is on the table. 0 joules. Here he is sometime later with something more than 0. We'll say, I don't know, 4 joules. Does 4 joules equal 0 joules? No. So is energy conserved? No. So have I just lied to you? I just told you this was the only truth in all of science, and then I just disproved it. What? What happened?
You said closed system.
Okay. And?
That's not a closed system.
Why?
I don't know what a closed system is, but
I don't know what it is, but I don't think you're being honest. Yeah, go. Right. I did stuff, right? In fact, you could say that I did what to it? Work. So I added energy to the system. Does that make sense? So if you talk about the system as the frog, then at the beginning, the energy initial was 0 joules, the energy final was 4 joules, and that change in energy had to come from somewhere, and it came from work that was done by who? Me. But if I'm part of the system, do we have potential energy right now? Yeah, I'm not talking about gravitational potential energy. What kind of potential energy do I possess right now that I'm going to impart on the frog now? What do I have?
Chemical.
Yeah. Yeah, because I ate my shredded mini wheats this morning, right? Yeah, so I consumed that chemical energy. Okay, so now from the point of view of this system of carboning and frog, right now we have some energy, 4 joules of energy, let's say. Okay, I have the 4 joules, he has 0. Now he has how much? 4, and I have 0. Or maybe I had 10, now I only have 6. Does that make sense? So if you look at the system, if we say that the system is carboning plus frog, then the initial energy, let's say, was 10 joules. The energy of carboning was 10, and the energy of the frog was 0. And at the end, the energy of the frog is 4. So we know now that I just used up 4 joules of energy. How much do I have left? I have 6 joules left, because the final energy still equals 10 joules. Is that okay? Okay. So it's all about what you define as the system. Generally, in the problems that we look at, it's going to be pretty easy to define the system. The thing that you need to know is that if work is done, it's not a closed system. Because if work is done, then the energy changes. So we're talking about closed systems where there's not any extra stuff being done. We okay so far? Okay. So we're going to do a couple of problems. This first one is kind of a theoretical situation. We've got a hill that is 8.2 meters tall, and I have a block that's sitting on the hill. There's the block. Okay. I want to know, I'm going to call that point A. Down here I'm going to call this point B. I want to know how much kinetic energy it has at A and B. I'm going to tell you that the velocity at A is 0. It starts off from rest, just barely going over. Okay, so this is like if you've ridden the tornado, you know, when you get up to the very, very top, you're like just barely going over, right? And then you start to move. It's the same kind of deal. And then at B, I want to know the kinetic energy and the potential energy. I also want to know the speed at B. And then here's the fun part of the story. I don't know if you guys have ever ridden. They don't have one of these at Adventureland, but some theme parks have situations where like you'll go one way and then you'll go back the other way. So this little roller coaster-like thing is kind of like that. Instead of having another hill, there's actually a spring at the end. Okay? And that spring gets compressed. Are you with me there? Okay? So the spring's going to be compressed, and the spring has a spring constant of 70.5. So I want to know how far that's going to compress. Okay? And we're going to assume, I'm not going to let you, we don't need to worry about this last question. We're going to assume that the track is frictionless, which means that it is a completely closed system with just the hill, the track, and the spring. Okay? I'm going to let you chew on that for a few minutes. Talk to your table mates. Talk about how you might approach it. I'll write some things down too, but I want you to see if you can figure out how to do a problem like this. go ahead and get started. I'm going to let you think for a couple minutes because I don't want to tell you everything. So a couple of little things on this, well, I guess on the second question, trying to find the speed of the block. There are a couple of different ways that you can approach it. You know that this is 1,000, right? So you can say that this is 1,000 is equal to 1/2 mv squared. You would need to plug in your mass. And the mass is not listed right now. The mass is going to be 122 newtons divided by 9.81. Does that make sense? So that's one approach. The other approach, the thing I wanted to point out to you, because this is important, is that if you look at this with a clever eye, you may notice that there's a mass on the left and a mass on the right. Do you see that? And so you can actually find the velocity. It's going to be the square root of 2gh. The mass doesn't matter. The mass of the block itself doesn't matter. This should be, and it's one of those things that if you're not thinking about it, you might not realize, but this should be a nice realization to you. Because otherwise, that would say that if I dropped the frog and I dropped the pen, they would have different velocities when they hit the ground. And we know from chapter 2 that that isn't the case, right? The acceleration is the same. This is actually just kinematics. This actually comes from the same stuff that we've been doing over and over and over. You just with a different kind of mindset. Okay? Either way works, and you'll get the same answer either way. I just wanted to point that out to you. Okay? So keep cruising on that. We'll check some answers in just a sec. I have in my notes, but I'm not 100% confident on it. Did you get something like 13 meters per second for the velocity? Okay. I'm not really worried about sig figs right now. And then I'm going to move this down just a little bit so I've got some space to do the last part, part C or whatever it is.
What was the coefficient? What was K?
Is 70.5. I will not move it quite down that far. There we go. So the energy at A has to equal the energy at C. That's the gravitational potential energy. So I'm going to write this out in good kid fashion. So KEA plus PEGA plus PESA is equal to KEC plus PEGC plus PESC So again, I'm just expanding this out like I did this one, acknowledging that there are all kinds of energies involved in the story. But again, I like to get rid of stuff like that and that. At C, it's going to be slowing down to a point where eventually it will what? Stop. That's going to be at its maximum compression. Does that make sense? It's going to go to maximum compression and then bing, it'll go back, right? That maximum spot, there is no gravitational potential energy, and because it's stopped, there is no kinetic energy. Right? So that means that 1,000 joules will all be in spring potential energy. Remember, that's that 1/2 kx squared thing. And I think from that, for x, I'm getting something like 5.3 meters. Does that match with what other people are getting? Okay, good. Sometimes I have my notes and I'm not sure if I change the numbers in something or whatever, so I want to make sure I wasn't being totally crazy. So there are a couple of answers. How's it going? Are we doing okay? Okay. Jake, talk to me. Okay, so you may need to go back and watch some of that video stuff, okay? But let me just give you the short version of it, okay? So spring potential energy is going to be stored energy due to a stretched or compressed spring, okay? So you can also think about it like a rubber band. So if you happen to have ever had a rubber band that happened to be between two of your fingers and you happen to apply a force over a distance, you're doing work on the system. Does that make sense? Yeah. And you're doing work, which means you're changing the amount of energy. You're adding energy to the system, and that's stored energy, and it's stored in the elastic band. Is that okay? So it's stored based on how much has been stretched. Okay? So there's the equation that we talked about last time was that spring, so we call it spring potential energy or elastic potential energy. In your book, they call it elastic, but then you have to write out the whole word elastic. That's a lot of work, so I'm just going to use an S instead. Okay? Is equal to 1/2 kx squared. And the reason for that is not really mysterious, but I didn't go through it with you guys. I'm just going to tell you and say, take more physics with me, and I'll tell you where it comes from. Does that make sense? K is how stretchy or not stretchy the spring is, right? Like if you have a really, really tough rubber band, it's going to be a whole lot harder to apply that force. Okay? If you have one of those crazy, right, then it's a wee, and then you can, that's going to affect how much energy is stored. And then the other piece is how far it's stretched. Does that help a little bit? Okay. What other questions can I answer for you right now? Okay. Doing okay? Okay. All right, I'm going to move on. I've got a couple more little problems for you to work on with this just to kind of make sure it's all sitting okay. They're practical problems, like bouncy balls, because bouncy balls are practical, right? Okay, so I've got a bouncy ball, and it's standing here, and I'm going to get a meter stick, 2 meter stick because I can. Rowan and I do read stuff, okay, so you need to pay attention very carefully. So we'll start it from, let's say, 1.5 meters. And we're going to talk this through before I actually do anything. Okay, so I'm going to start it from 1.5 meters, and if I was going to write down a total energy equation, right now I would say that the energy is what kind of energy?
Gravitational.
Gravitational potential, is everybody okay with that? It's going to fall. As it falls, what happens to the gravitational potential energy? It goes down, right? MGH, my H is getting smaller, so my potential energy gravitational is getting smaller. And is that energy just going into nothing? It's turning into kinetic. Does that make sense? Okay, so it's turning into kinetic. At the bottom, it's now all what? Kinetic energy. And then we've got, and so then it's also going to bling, right? It's going to bounce back up. So it's going to, there's actually a little bit of an elastic force that happens in there, which is why it doesn't just stop. It bounces back up. And if everything was perfect, how high should it bounce?
1.5.
1.5 meters, right? Does that make sense? Yeah. So then we test it and we find out if that's really true. So is it, look at, it's about 1.5 right there? Okay, so then I need you to watch and see how high it goes. We're going to hope for 1.5 again. So here we go. 1, 2, 3.
Like 1 meter.
Like 1 meter, she says. Okay? What's up with that?
Some of the energy went into the floor.
Some of it went into the floor because the floor is not part of our system. Does that make sense? So my question for you is, how much energy was lost to the floor? Okay? How much energy was lost to the floor? So let's write down the things that we know. It starts off with a height of how much? 1.5. And it falls, and then it bounces up to a height of, we said, 1 meter. Okay? I want to know how much energy is lost. What other information might you need to know from me?
Acceleration.
The acceleration due to gravity, I bet you can figure that out.
Yeah, mass.
You need to know the mass. I'm just going to kind of guess for a minute here. I'm going to say it's about 13 grams. I'm going to go measure it real quick because I'm curious. Because I'm guessing I'm actually totally wrong. Now I'm going to guess 20 grams. I'm going to guess 20, but I'm going to measure. You guys get it set up because you don't need the number until the very end. So you get it set up and figure it out while I measure them. See how poorly. Oh, it wasn't terrible. 27 grams. 7 grams off, that's not bad. 27 grams. So I want to know how much energy is lost to the floor. Does that mean the energy is lost forever? No, it's just imparted onto the floor, right? So it depends on what you're calling your system. Are you calling your system just the ball or the ball on the floor? So the initial height was, what do we say, 1.5 meters? And the final height was 1 meter, 27 grams. And I want to know what the change in energy is. Talk to your table mates. I bet you can figure it out. How are we doing, team? We doing okay? What do you mean?
Can we just say work, or do we need to show that? Or you have right now?
Like, what are you proposing to skip? Like, I guess let me answer the question not in a direct way because there's not one right answer. If you were doing a question like this on a test and you just had your givens and those numbers, I would have no idea where they came from.
So what I was saying was change in energy is equal to work, and then I put the work equation, and then I'm doing that. Would that be a bad way to do it?
Yes, because you don't know what the force is and what the distance is. Because the distance is actually like how far did it rink down like that. You with me there?
Yeah.
Yeah, so this is the more direct change in energy thing. Yeah. Does that make sense?
Yeah.
Yeah. You don't know what that force is. Are we doing okay besides that question? Other questions? Are you guys getting numbers that look like these?
Oh, yeah.
What if we got the same answer that we did in the work equals change in energy?
So where did you get your work from?
I did, what was work initial, and we did work doing final.
What do you mean work initial and work final?
Like from the different heights.
Yeah, I did the work.
Okay, so what you're doing. Okay, so let me explain why I wouldn't do it that way. Really, what you've done is to tell me how much work would be done if I take this thing and I move it up to here. So you're telling me the difference in energy, but the work is not that force times distance. The work that's actually done is the force of the floor times the distance. If you've ever, I don't know if you guys have ever watched like a racquetball. I don't have the slow motion video, I wish I did now. But like a racquetball hitting a wall, you can see it like, and it like changes shape a little bit. It goes, and there's like this little like flat spot. Do you know what I'm talking about? Have you ever seen this? That's the distance. And the force is the force of the wall, or in this case, the force of the floor. So while you're getting the same numbers, you're not getting them for the right reason.
Okay.
Do you see what I'm saying? Yeah. So the numbers would work out, but if I was grading that question on a test, I couldn't give you full credit for it because even though it works out, the physics isn't right. Yeah.
That's why when you kick the bounce a little harder against the floor, it goes higher.
Right. Right. Well, in that case, too, it's got more energy to start, right? Because it's got kinetic energy. Mm-hmm. So what are we getting for a change in energy there? What'd you get? Something like that? Is that okay?
And that came from subtracting one from the other.
Yep, exactly. Given the time and the short day, I'm not going to spend a lot of time with this, but I just want to show this to you. I don't know if you guys have ever seen one of these before. But it's like a half of a bouncy ball, which is kind of fun. But the more fun part is that you can go like that. And by doing that, so right now if I drop this, it's going to be just like a regular bouncy ball, right? Nothing super exciting. I drop it here, it's going to go down, and it's not going to come up very high. But by going like this, what am I doing to it?
You're going to get more spring energy.
I am. I'm applying a force, right? Over a distance of like 2 centimeters, but it's a pretty decent little force that I have to apply for that little distance. So now, when I take this thing right here, what kind of energy does that have? Gravitational potential. And is that the only kind?
No.
No, it's also got what?
Spring potential.
It's got elastic or spring potential. And so now, I don't know if you guys have ever seen one of these before. I'm going to hold it down here. And sometimes it doesn't work the first time because, physics never works the first time. So I'm going to go like this and I'm going to drop it. So right now it's got, we said 2 different kinds of energy. It's going to fall. And then when it hits the ground, what kind of energy does that have?
Kinetic.
Just kinetic?
Yeah. Kinetic and spring.
And spring potential. But that's going to pop and it's going to pop and then we'll see what happens. So I'm going to start it from here. Here we go. Oh. So again, it seems to defy this conservation of energy thing that I've told you is true, right? It's always true, but did I really defy physics? No, because I've done work to the system, right? So you have to be able to account for that. Now we've got those 2 kinds of energy again, because it's just kind of fun to watch it one more time. So it starts here, and it bounces up much higher than it started, because when it gets to that very top spot there, what kind of energy does it have? What? What'd you say? At the very top?
Gravitational potential.
It's just up at the very top. Is it moving?
No.
No. So does it have any kinetic?
No.
No, it's just got what? Potential. It's gravitational, right? Does that make sense? So we can do the math with it. I'm not going to do it right now because we don't have a lot of time, but I do want to show it to you because it's kind of fun and I was like, whoa, that's weird. All right, we've got what, like 10 minutes. I've got a couple of problems from the book that I'm very happy to share with you. I also want to make sure that there's time to go over homework. So let me ask first, are there homework questions? Are there things that you would like help with from the homework? Okay. I'm going to write down, just so that you have them in case we don't have time to go through them later, the 2 problems from the book that I was going to tell you, and I'm going to tell you the answers to them so that you can go through those on your own. They were on page 185, number 2, and number 5, and let me look up the solutions to those real quick for you so you can write those down. And as I'm doing that, if you guys want to pull out your homework questions, then I'll answer those questions here as well. All right, so 185, question number 2. There are 2 questions apparently. 9.9 meters per second, and then 14.0 meters per second. Just watch what? What did I do? Did I mess you up?
What are these problems for?
These are just conservation of energy practice problems. If we had a full block instead of just this early out block, I would have had you go through these in class and work through them and that sort of thing, but I'm watching the time tick, tick, tick away. Okay, so these are just, if you want to go through them, great. If you don't, that's fine, but these would be good practice to do. Okay. All right, homework questions. I am ready. Hopefully you have a textbook in front of you. If you don't, make it so that you do. Mitch is either stretching or has a question. I'm not sure which. 4?
34.
34. Let me take a list. Yeah. 33. And I'll take anything from chapter 5 that you need help with. 20. Anything else on the list right now? Cindy, go ahead. What'd you say? 23. Others? 24 part C, she says. Okay, let's do it. I'm going to start with number 20, because that's the first one. So I'm on page 194. Hopefully you are as well. Number 20 says, what speed would a fly with a mass of 0.55 grams, we pay attention to the fact that it says grams, need in order to have the same kinetic energy as the automobile in item 19. Did you guys do 19? Or is this a really annoying thing that came from Schoenberg from ever ago and I forgot to fix it?
We did 19.
You did 19. Okay, so you know how many joules are in 19. Cool. So now for number 20, you're just going to say that the kinetic energy is equal to whatever it was from 19, which I can look right here, is 7.6 times 10 to the 4th. Does that look right? Joules is equal to 1/2 mv squared. And you know the mass is really little. So it's 0.55 grams. So if you're going to write that as kilograms, then you need to move it over 3 more times, right? And then solve that for V. So I think V is going to be equal to the square root of 2 times the kinetic energy divided by the mass. Is that okay? Did I go too fast? Does that algebra make sense to you, what I just did there? Does that get you where you need to go, or was there more of an issue on that one? Thinking. I'm going to keep going if that's okay. Let me know. 23. A skier at the top of a I can't speak. Slope, as in a picture. Initial point A. The skier is 10 meters vertically above the final point at B. And then this is basically like the problem that we did with the frog falling from above the table, where you're setting your h equals 0 at different places. Okay? So on number 23, you've got a hill, 15.8. I bet that there's a picture in here somewhere. Or 518, excuse me. I speak well. Can you tell? 518. What page is that on?
Isn't it under the...
Oh, it's right there. It's just sitting right there staring at my face. Thank you. Okay. And we know that this distance is 10 meters. In part A, it says to set the 0 level at B. So H equals 0 here, which is what we probably would do normally. Then in part B, it says set H equals 0 up here. And then part C says, okay, be wild and crazy, and set H equals 0 in the middle. Regardless, the change in energy is going to be the same, right? It's just wherever your 0 point is. That's all that they really want to get you at there. Is that okay? Does that make sense? I'm going to keep going if that's all right. Pretty happy? 24 is the same kind of question again, just with some more numbers. A 2 kilogram ball is attached to a ceiling by a 1 meter long string. I don't know why. The height of the room is 3 meters. What is the gravitational potential energy associated with the ball at different points? So for 24C, so here's my room. There's the floor and the ceiling. This is, what was it, 3 meters? And the ball is hanging like this. That's 1 meter. And it says a point at the elevation the same as the ball. So if H equals 0 there, then what is the potential energy?
0.
0. Because MGH, H is 0, so it's 0. That's all it is. Yeah. H can be 0 wherever you want it to be. You have the power to make that decision. We okay there? I know I'm going fast, but I want to make sure we're okay. Speak if you have a question. All right, 33. Oh, yes. 33. A child on a sled, combined mass of this, slide down a frictionless hill that's this high. Starts from S. Hey, you just did this problem. This is like the first problem we just did, right? Different numbers. But it is exactly this problem. There's just no spring at the bottom. Wouldn't that be kind of fun if you were going sledding and at the bottom of the hill there was a nice cushy spring? Because where would that send you? If this box goes down here and hits the spring, where's it going to go? Right back up to the top. Then you don't have to climb back up the hill, right? Like, how nice is that? It's a sweet gig, and then you just keep going. Whee! Right? Like, forget all those other kids that are in line. You're just going to keep going back and forth. That's great. Same kind of thing on number 33. Is that okay enough of an answer, or do you want me to go through more of it than that? You guys are so quiet. I don't know what to do. I'm taking your silence to mean that you get it, unless you say something otherwise. Okay. All right. Last one was 34. 34 is Tarzan. Yay! I love this question. All right. We did a problem kind of like this at the very end of class last time with the little girl on the swing. There's one piece of information that's not in this question, though, and it often freaks people out. What do you think is missing? The mass, right? But it's not missing, friends. You can do it without the mass if you write the equations out. If you write it out. So here we go. So here's the branch. Here's the vine. Here's Tarzan. Okay. 30 degrees. So you got to draw your little triangle, the same little guy that we had before, right? Whee, there you go. Because you want to know that height there. So that piece you need to know, because he's going to end up down here. apparently changed color while he was swinging. That's exciting.
Just the lighting.
Right, there you go, yeah. Shading was different. On the, it was nice open area there, and that's you're right underneath the tree, right? So there you go. Okay. We want to know how fast he goes to the bottom. What kind of energy does he have up here? Does he have any energy there? You could say gravitational potential if you said H equals 0 here. So if we look at it, I'm going to call this point A, I'm going to call this point B. So I've got the energy at A has to be equal to the energy at B. So I've got gravitational potential as an option. And at the bottom, what kind of energy is he going to have? Kinetic. Whee! Right? We're going through a swing there. So this would be a really good way to write this down. Oops. Should be a KE. At the top, he's not moving in part A. In part B, he is. So that's going to be the difference here. You get rid of that for part A. For part B, you have to write 1/2 mv squared, right? Okay. At the bottom, if we said h equals 0 there, then that one's for sure going to go away. This is mgh A plus 1/2 mva squared is equal to mgh B. And if you look carefully there, there's something in every single one of those terms. Oh.
Is this for A or for part A?
This is a general statement. So for part A, the kinetic energy is going to go to 0 in A. Yeah. So the masses will all cancel, which again is nice because then if you have Tarzan who's really, really large or Tarzan who's really, really small, it doesn't matter. They're going to go the same speed at the bottom.
Is that mv squared, 1/2 mv or mg?
mv
So
squared.
we cancel out all the m.
Yeah. Divide by m on everything and the m's are gone.
Kid Tarzan or adult Tarzan?
All right, make sure the textbooks get put away, please. All of the textbooks on your tables go back in the back by Emma. Have a great day. I'll see you on Friday. The homework is due on Friday, test on Friday. We'll see you then. Have a great day, guys.